And so I will get started here. So welcome everybody to our 8th seminar in the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce you tonight's speaker, Jorge Zanelli. Jorge is currently a senior researcher at the Centro de Estudios Científicos, that's CECS, in Valdivia, Chile. Jorge completed his PhD at Stony Brook and managed to sign on at CECS in 1985 after just one postdoctoral fellowship at the ICTP in Trieste. Jorge is perhaps best known for a black hole solution in 2+1 dimensions that he found together with Bañados and Teitelbaum in 1992. He's the Z in the BTZ black hole. Jorge's main research interests include black holes, Chern-Simons systems, and supersymmetry. So today, Jorge will be telling us about an unconventional version of supersymmetry he's proposed with collaborators. This new setup connects spin 1/2 fermions and spin 1 bosons, and as a result, could be more readily compatible with the standard model. I should mention that it also offers a natural entry point for gravity. Now, before we begin, I'd like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it's not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Jorge, anytime you're ready.
Okay, thank you. Okay, let me share the screen. Can you see this?
Yes.
Okay. Well, first of all, thank you very much, Nichol, for inviting me to give this seminar at this exciting group of people who have been following for the past few months. And I think that it's a privilege to be able to present my work on this group. So, well, this work has been going on for about 10 years now. And there is a number of collaborators that I wrote down here. The people in blue are from Chile, and the people in green are from Torino. And it's a long standing collaboration with them that has started about 5 years ago now. So what I want to present to you is my interpretation of what supersymmetry may be good for, because you've probably seen that supersymmetry is a sort of a backwater of particle physics nowadays. It's been going on for about 50 years now, but it's not given all the results that people expected them. So let me begin by telling you what is that I think it's going to be a use for supersymmetry. Well, supersymmetry is supposed to be a symmetry between bosons and fermions, in which, according to Wikipedia, for each particle there is one class, fermion, there is another associated particle of the other class. And it's these superpartners is a hallmark of supersymmetry. And this comes from a representation which is essentially written here, that you have bosons and fermions in a multiplet, and there's a Q operator, a supersymmetric operator that sort of mixes them. This idea was started maybe more than 50 years ago by a group of Russians and some people in the US also, who discovered this from the algebraic point of view, and then they were trying, and the people in the US, they were trying to find a unification between internal symmetries and space-time symmetries. Now, supersymmetry had a number of features that make it very attractive. And when I was a graduate student, this was the hot topic, and everybody was in love with supersymmetry. It justifies the existence of fermions and bosons. They explain why you need both. It restricts in a very subtle way what particle multiplets can exist. It relates masses and coupling constants of particles. In all the supersymmetric models, these things are constrained very much. It provides positive energy theorems for for most theories, including gravity, and therefore it may explain why this particle systems may be stable. It gives stability to the situations, to the models. It also improves renormalizability because there is a cancellation, there are magical cancellations between bosonic and fermionic divergent terms. And also it provides some protection for mass scales, and therefore it respects or explains hierarchies. However, after 50 years of experimental search for this, there is no single evidence of supersymmetry that has been found. And this is something very mysterious. Why? Well, let me begin by saying what supersymmetry expected to solve. Why was supersymmetry introduced? Well, in the 60s, there were these two aspects of symmetries in entering into the pictures of particle physics. Wigner, already in the 30s, had classified particles by their spin and mass, so representations of the Poincaré group. And in the 60s and 70s, it was clear that there were other groups, or other symmetry groups, internal symmetry groups that were relevant, especially color and SU2 symmetries. There were approximate symmetries, but there were internal symmetries that also were useful to classifying particles. So the idea was that maybe one could find a larger group which contains both internal and spacetime symmetries, and the classification of all states and particles could come from this unified picture. So they were looking, they looked for groups that unified internal and spacetime symmetries. But then in 1967, after many years of frustrated efforts, Coleman and Mandula came to this no-go theorem that explained why this wasn't feasible. They found that if you have an space-time symmetry and internal symmetry together in a larger H group or a symmetry group for the S matrix, this could only happen if these two groups were trivially combined, namely the symmetries were independent symmetries, or the Lie algebra was essentially a direct sum of two Lie algebras, and there was no fundamental unification of the two. However, a few years later, not only perhaps 5 or 6 years later, there were some discoveries like this strange paper by Volkov and Akulov that came in 73, in which they found a symmetry that it was a combination of internal and space-time symmetry. The Lagrangian they proposed in this paper was invariant under time translations simultaneous with shifts in the Fermi field of the Lagrangian. And this seemed to violate the Coleman-Mandula theorem. And indeed it does violate the Coleman-Mandula theorem, but it was not clear why. Then in 75, Hayek and Lopushansky and Sonius came with an explanation for this mystery. They showed that if you have an internal symmetry and a space-time symmetry that commute among themselves, you could add another ingredient, some fermionic generator, which had non-trivial commutators with both internal and space-time symmetries, and in a way that the whole algebra closes in a non-trivial manner. That means that space-time engaged or internal symmetries could be part of a graded Lie algebra rather than just an ordinary Lie algebra. And this is in fact what Akulov and Volkov had found. It was an example of this type of symmetry. So then there was an explosion of research in supersymmetry, and most supersymmetric models came to be represented in this manner, where you have bosons and fermions, and under supersymmetry they would mix into a new boson and a new fermion. The typical supersymmetric models were rigid or global supersymmetries, And the first models by Wes Sumino, Salam, Strathby, Leopoldo, Schiffman, many other people were looked at was essentially an supersymmetric extension of the Poincare algebra. In the Poincare algebra, on the Poincare supersymmetry, usually the commutator of these supersymmetry generators is proportional to the Hamiltonian, and the Hamiltonian commutes with the generators of supersymmetry. This means, in particular, that since the mass of the supersymmetry is essentially the eigenvalue of the Hamiltonian, that means that there would be particles, bosons and fermions, that would have the same mass because they would be degenerate in energy. And also, it was clear from this picture that for every bosonic state you would generate a fermionic one, and vice versa, that the number of bosons and fermionic states would be equal. Now, none of these two things are seen in the experiments, so supersymmetry must be severely, badly broken. Also, well, this was a signal of supersymmetry that is not being found, but to me, there may be even worse conditions for supersymmetry, or the more unlikely things in supersymmetry than just this. After all, you could imagine that there are bosons and fermions in some cases in which they have the equal mass. For instance, a photon and a neutrino, like Akulov and Volkov proposed, in which you have two particles, one boson, one fermion, with equal mass. But this is not a generic thing, and it seems to be the only case in which a boson and a fermion share the same mass. But nowadays, even that is not so clear, because neutrinos have been seen or are expected to have a very tiny mass, but non-zero. Anyway, this is a situation with standard supersymmetry, rigid supersymmetry. Now, even already in the 70s, there was some skepticism about this, and the first expression of this I heard was by Paul Dirac, who mentioned to Salam in a conference that if this symmetry existed, it would have been discovered a long time ago. So he was extremely skeptical about the existence of such a symmetry between bosons and fermions. Well, if you try to push the idea and try to accommodate particle physics into a supersymmetric model, the so-called standard supersymmetric model, for each observed particle, you have to include a partner of the opposite statistic. So for each quark and lepton, you should have an S quark and an S lepton. And for the Higgs, you would have a Higgsino and so forth. So there's, for every particle that we know of, which were observed in accelerator and experiments, there will be all the other particles that we haven't seen. Not only that, this was proposed to be a solution for instance, the dark matter riddle in cosmology, because these particles that have not been seen maybe still gravitate, and they therefore could account for dark matter. But this fact that you have for each particle a superpartner requires that, since you haven't seen the superpartners, these superpartners must be extremely heavy. And then there must be a mechanism for supersymmetry breaking, which is not clear what it is. And there's not even a reason why this supersymmetric partner should be so heavy. Now, if you try to accommodate this into a Lagrangian for a standard model, you end up with a system that has more than 100 new parameters to fit all the information. And this is in very bad news, because in the standard model, there are only about 20 parameters among the masses and the coupling constants. Here you would have more than 100. So supersymmetry, it's not only a solution to a problem, it creates many problems as well. So, but in the 90s, there was still some optimism about supersymmetry. And these authors say that in a paper in 96, that the discovery of supersymmetry in particle physics together would rank with quantum mechanics, special and general relativity, and gauge theories among the most important discoveries of the 20th century. Well, that didn't work in the 20th century, and also there was some skepticism growing in the first decade of the 21st century, because the experiments and the starting of the LHC that did not find anything created the sentiment that perhaps supersymmetry was dead. Now, what I find most what I dislike most about supersymmetry is not the fact that you don't have equal masses for particles and bosons, for bosons and fermions, but the fact that bosons and fermions play very different roles in nature. Fermions are particles that are not created or destroyed. They exist forever. They are created, when they're created in pairs. And so the number of bosons, the number of fermions is always a constant. However, the number of bosons is not, because you can create as many as you wish in any point in space-time. And also the roles they play is very different. Fermions are sort of the sources, and the bosons are the interacting fields or interaction fields that mediate the forces among particles. So they have different functions in the standard model. And to assume that bosons and fermions can be interchanged means that you would have carriers of interaction with fermions, and you would have particle sources or matter sources which would be bosons. And we haven't seen any of that. What we have seen is particles of spin 1/2 for fermions and particles of spin 1 for bosons, and that's it. And they have the roles that they play in this model. So if you make a list of what fermions and bosons do in the standard model, they have a number of features that are very distinct. And to assume that they could be exchanged is something of a violence in the model. So I think that this is the main reason why it's very hard to make a viable supersymmetric model in this way. Fermions have spin 1/2, bosons spin 1, fermions are gauge vectors, or they correspond to sections in the fiber bundle. Bosons, on the other hand, are connections, so they are in different representations. This is a fundamental representation, these are in the adjoint. And fermions are space-time scalars, they are zero forms, whereas these connections are space-time vectors or one forms. These are Lorentz spinors, these are Lorentz scalars. These obey first-order differential equations, this obeys second-order differential equations. So it's very hard to imagine that these features can be exchanged. So the wish list for a supersymmetric model would be to have a way to combine bosons and fermions under some hopefully local symmetry that would respect the roles of connections and sections in a fiber bundle, for connections for bosons and sections for fermions, that would have the right kinetic terms for fermions and bosons, the typical kinetic term for first order derivatives and the second order of first derivative square for the bosons, and the right couplings, Yukawa type couplings. We expect that there will be no duplicate fields, no super partners, so for every boson may not be a fermion and vice versa. This theory should allow for massive fermions and massless bosons, because this is what we see in the standard model mostly. Should contain only spin 1 and 1/2. That's all you need, because the rest can be composites of the spin 1 and spin 1/2. For instance, scalars could be particle and antiparticle pairs and so forth. And it should also allow for a curved and dynamical spacetime, so it should allow for gravity. Now, most of these features are violated by both supersymmetry and supergravity, except the last one, which is valid for supergravity. But none of this is true in the case of standard supersymmetry. So what is the idea of the unconventional supersymmetry? Well, the first thing is how to combine fields of different representations. Bosons and fermions, we said, are in different representations. Bosons come in the adjoint, and fermions are in the vector. So how could you combine an adjoint and a vector representation into a representation of a gauge group? So the idea is that you cannot do always the following. You have an adjoint representation, for instance, of SO3. So you have an antisymmetric 3x3 matrix representing this adjoint, and a fundamental representation, so it's a 3-component vector. But you can always take these two and put them into an array, which is a 4x4 antisymmetric array, which is the adjoint representation of SO4. In this way, you embed the SO3 group into the SO4, and you accommodate the two representations here into one representation here. And this is an adjoint representation. So if you have a connection and a vector, you may be able to put them together in another connection of a larger group. That's the basic idea. So this allows to combine connections and vectors of a given group into a connection for a larger group. So for example, if you have an internal gauge connection A and a spinor chi, and a Lorentz connection, let's say this Lorentz spin connection, omega AB, you can accommodate them into one connection, which contains the generators of these three groups, the gauge group, the supersymmetry corresponding to the fermion, and the Lorentz generator. And this is a connection if this A, chi, and omega are one forms. If you want this to be form an algebra, you need that the commutators of k, q, and j close under commutators or anti-commutators, so in a graded Lie algebra. So you may need to add more generators to close the algebra, but that will depend on the dimensions of these objects. Now, this idea is still rather conventional because it's essentially what McDowell and Mansouri proposed in 1976 for constructing a supergravity model in 4 dimensions. They assumed the anti-de Sitter group here, besides the Lorentz generator, they also included the rest of the generators for the anti-de Sitter group. They included the supersymmetry generator, and they allowed for some internal symmetry, but it was not necessary. However, this model didn't quite work in the way they expected because it didn't produce exactly the supergravity model that they expected. There was some issues about it. So this idea was somehow abandoned, but it was an interesting proposal. Also, this idea was put forward by Achúcarro-Townsend in '86 as a way of constructing Chern-Simons theories for supersymmetric models or supergravity in odd dimensions. And this idea can be applied for any supersymmetric Chern-Simons theory in any number of odd dimensions. Now there is an issue here. In order for A to be a connection or one form, the spinor chi must also be in one form. So it has an index mu. Besides the Lorentz index, it has this other index. That means that this is in a representation with spin 1/2 plus spin 1. So it's a spin 3/2 object. And this is what gives the gravitino in supergravity. But this particle with spin 3/2 is not part of the standard model, and we have not seen it anywhere. So one idea was to assume that this object that has both a spin and a vector index, or a spin and a one-form index, could be a composite of two things. Could be a gamma matrix and a fermion of spin 1/2. So this ansatz is what we call the matter ansatz, is in which we change or we exchange the gravitino field for a matter field with spin 1/2 matter field. Now this matrix here is actually a composite of the gamma matrices or the Dirac matrices that are representations of the Lorentz group in the tangent space, and something that projects the tangent space onto the base manifold, so that this is a one form, and this is essentially a soldering form or a field bind. So if the theory allows or contains a metric structure, a field bind, you can always do this. You can always add combine the Vielbein and the Dirac matrices and produce the Dirac matrices as one forms. Now with this, you can put everything together because now you can insert here this would be a gamma mu times some spin 1/2 field, and this would be a one form again, and therefore this would be a well-defined connection.
Can I ask a quick question?
Sure.
Yeah. Would there be a way of knowing experimentally that the say standard model fermions are forming these composite 3/2 representations?
Experimentally, well, the only dynamical field here would be the two dynamical fields. There is this spin 1/2 field that would obey something like the Dirac equation, and there would be this Vielbein that would be part of the geometry of space-time. So if you could, this, as we will see, this will be part of the gravitational sector of the theory. And therefore, this theory will contain, in a very fundamental way, the information about the geometry of the background, besides the fact that there is matter living in it. So if you want to experimentally probe for this, you will need to have experiments that measure or are sensitive to the geometry of space-time. And I don't know whether experiments in accelerator physics, for instance, could do that.
Okay, so there would be no way of, say, measuring like a composite spin 3/2 particle, for example.
Not in accelerator physics, maybe in another indirect way, like in cosmology or some other structure, but not in high energy experimental physics. I wouldn't say that.
Okay.
Thank you. So take, for instance, an example, the simplest example is in 3 dimensions. You could have an internal symmetry like SU2, for instance, a space-time symmetry, which would be the Lorentz invariance, and the supersymmetry generators. And this would be the connection with the spin 1 connection for the internal symmetry, the spin 1 connection for the Lorentz symmetry, and the spin 1/2 fields for the supersymmetric part. Now, these would be the bosons, and these would be the fermions. These are 1 forms, the fermions are 0 forms, and everything sort of fits in what we know of the real particles in the standard model. So for instance, in the case where this is SU2, this is SO12, and this is supersymmetry, this form a superalgebra of SU1, 2 bar 2. And this is the algebra. This is a connection in that case. And if you with this connection, you construct the Lagrangian, then you're done. That's the end of the story, and you use all these symmetries and study scattering cross sections and so forth. Now, all these fields are scalar under general coordinate transformations because they are differential forms. Therefore, general covariance is automatically built into this model. Moreover, this model contains a Lorentz group, and so an affine structure, and a metric structure here in the Vielbein. So somehow all this contains gravity. So in the metric structure that has to be put in order to accommodate for fermions, you have already all the ingredients that you need for gravity. And as we will see, gravity emerges in these models. So let's see what the action looks like. Now, if you want to write down an action for a connection, there are essentially 2 options. One option is to use a Chern-Simons action, which is good for any odd dimension. And also you can use a Yang-Mills action, which could be good for any even or odd dimension. Now, in the case of a Chern-Simons form, all you need is the connection and this bracket, which is invariant trace in the algebra, or in the superalgebra in this case. In the case of Yang-Mills, you need also the invariant trace, but you also need an object, which is the Hodge dual. Without this, you don't have a well-defined action. Now, the Hodge dual again is defined with a metric. So if you assume a metric structure, then this is all you need. You already have assumed the existence of something like this. So the simplest system that you can construct is the Chern-Simons theory in 3 dimensions, which has this form. For instance, for the case I mentioned before, the SU2 cross SO12 cross the Dirac gives you this. It's a Lagrangian that has a form of Chern-Simons term for SU2, a Chern-Simons term for gravity. This is omega, the omega plus 2/3 omega cubed, and a fermion that satisfies essentially a Dirac Lagrangian with the minimal coupling, with the minimal coupling to A and a minimal coupling to the Lorentz connection. There is a question? Yes, please. Tejinder, please switch on your microphone.
Okay, here I need to, here we go. Okay, yeah, Tejinder?
It's microphone.
Yes,
okay.
yes, it's unmuted now. Sorry to interrupt you, very sorry.
Okay.
I just had a sort of conceptual question, which I have also bothered about. It's so far so good. But when you look at this Lagrangian, it in no way shows an evident symmetry between how you construct a Lagrangian, an action or a Lagrangian for the bosons and for the fermions. Already in some conceptual sense, I see a divergence. So I imagine something like a plus f whole square, suitable derivatives put in. This is already showing some kind of a harmony between the bosonic part and the fermionic part. What I would have called genuine supersymmetry should be staring at me in the eyes when I write down the action. Do you have some thoughts on that?
Yeah. Okay, this is a completely different construction from the standard Wessumino type of approach. Here, the whole invariance of the action of the supersymmetry is contained in the algebra. Let me see if I can show you next slide. Yeah, here is the, I'm sorry. Here's the connection. Mm-hmm. Now, these generators, well, this is in 4 dimensions. Let me go back. I'm sorry. Yeah, here is the connection for the SU, but the 3-dimensional case. If you take this this connection, and transform it as in the adjoint representation as a connection, so A prime would be the derivative of a parameter with some inverse matrix times the on the left-hand side, plus something like A commutator with the parameter. So if you transform this A as a connection within the same algebra, then you would find the transformation of each of the components, this bosonic term, this Lorentz connection term, and the fermion would be derived from that expression. If you substitute that expression in the Lagrangian here, you would see that the whole Lagrangian changes by a boundary term or by a total derivative. So the invariance is built in under the most general transformations of the entire algebra, including supersymmetry, of course, as a particular case. So if you take a transformation with a parameter that is only along the supersymmetry generator, this action is invariant up to a total derivative. So the way the supersymmetry is implemented here is a completely different form from the standard Wessumino approach, where vectors transform into bosons in a sort of vector representation, where bosons and fermions rotate into each other. Here there will be also a combination. I mean, the change of, for instance, the change of this field will be proportional to this field and the parameter with some derivatives, and so forth. With all of them, there will be some expression like that, but it's not a simple representation like a rotation in the case of, as in the case of the Wessumino model. So it's very hard to see that this is invariant under supersymmetry. I mean, it's not obvious that it's invariant under supersymmetry. In the same way that it's not obvious that, for instance, this piece here is invariant under SU2, because these are not tensors of SU2, these are connections. So you have to do the exercise and see what happens when you change this under SU2, where A is a connection of SU2, and you will see that this transforms by total derivative again. And this is true also for the Lorentz part and so forth. So it is not obvious, as you observed, but it is true that you can check that the Lagrangian does change by a boundary term when you do that.
Okay, thank you. Thank you.
Sure. Okay, well, this Lagrangian, if you do this for SU2 or for U1 case, which is even simpler, this Lagrangian turns out to be the long wavelength limit of graphene, which includes curvature of the graphene sheet, includes torsion in the graphene sheet, and SU2 coupling of this thing. And the bosonic part are not propagating fields because they satisfy some, they're essentially topological. They satisfy the Chern-Simons propagating equations, which are essentially topological. And the only propagating degree of freedom here is a fermion. So it's like a spin 1/2 particle interacting with this background made with curvature and some gauge fields around. There is a question by Andres.
Yes, exactly. Andreas, please go ahead. No, it always takes 2 tries for some reason.
Okay, yeah, can you hear me? Yeah. So
Yes.
follow up to this last question, maybe, but I also wondered that before. So does it mean in your construction that automatically the internal symmetry is, there are symmetries, right?
Sure.
Yeah.
Yes.
So it's
There are
unavoidable, right?
Yes, they are gauge symmetries. Yes.
Yeah, but they're gauge, but they are also, I mean, they act differently on fermions and bosons, right? This is
Yeah, sure. For instance, the SU2 symmetry under SU2, this A transforms as a connection, but this doesn't transform at all. This commutes with that.
yeah.
And the fermion transforms as a vector representation or fundamental representation of SU2. Is that what you?
Yeah.
Yeah. Okay.
Thank you.
Yeah, that's the beauty of it. I mean, the bosons and fermions transform in the right way under the internal symmetry group. Yeah. Any other question? Okay. Now, so the field equations in this case will, for the connection field, has a standard form of Chern-Simons. So the curvature is proportional to the source, to the current. For the gravitational part, the curvature is proportional also to some source, which is like a energy momentum tensor or something. And for the spin 1/2 field is the Dirac equation. And if you vary the action with respect to the field band, you get essentially the T mu nu, or the energy stress energy tensor. Now here there is this parameter mu, which is comes from the fact that there is a coupling between the fermions and the torsion. And the torsion is the one that gives rise to this parameter mu, which is a fermion mass. Now this fermion mass is essentially an invariant, which is a contraction between the background of the geometry, the torsion background of the geometry, and the field line. So in this case, the bosons remain massless because they're topological fields, but anyway, the excitations would be massless, but this may acquire a mass depending on the background. This you can show by the equations of motion that this parameter actually has to be a constant, because the torsion is covariantly constant. Therefore, this mu ends up to being constant. Anyway, there is another example that I want to show you. It's in 4 dimensions. You can play the same game. In this case, you could have you need more bosonic generators in order to close the algebra. You need to include both an internal, for instance, SU2 and U1 connection, And besides the Lorentz connection, you need to include also the special ADS transformation. So you have the SO32 anti-de Sitter group for the spacetime symmetry. Well, the anticommutator of the supersymmetry generators closes on the internal symmetries and the spacetime generators. And the curvature has this form. And then you turn on the crank and try to construct a Lagrangian. And to construct a Lagrangian, you need to have, you need to have some ingredients like you need to introduce this Hodge dual. So the Lagrangian takes the form of essentially a Yang-Mills form, where you have this Hodge dual, which in the internal symmetry transformation is just the star, the ordinary Hodge. For the fermions, for the fermionic part, here is the gamma phi term. And for the space-time part, essentially here is essentially the epsilon symbol. With this thing, you can construct the Lagrangian, and one thing that one sees immediately is that Fa, the generator, the field that goes in, the field that goes together with the generator of the special ADS transformations or ADS boosts is no longer a gauge field, it's an auxiliary field. And this is because this Lagrangian now is not invariant under gauge transformation for the whole group, but only for a subgroup. This is the largest subgroup for which you can construct an invariant in 4 dimensions. And this is the form of the invariant. And you can see that this part is no longer a symmetry. This Lagrangian is not invariant under the generator, and the local transformations with the generator that goes along this field. So this field is no longer a gauge field, it becomes an auxiliary field. So it satisfies an algebraic equation. In this case, the fact that there's no OSP42 symmetry in invariant action is because there are no invariant traces in 4 dimensions for this group. There is not even an invariant trace for the anti-de Sitter group in 4 dimensions. And therefore, the largest symmetry group that has an invariant trace is this subgroup. This is the largest subgroup. It contains the SU2, contains U1, so it contains all the internal symmetries, and it contains the Lorentz symmetry, but it doesn't contain the other spacetime symmetries or supersymmetry. I think that there is a question.
I believe that was Andreas from last time. I'll unmute him. Andreas, okay. Did you have another question?
Oh, no, I think I just forgot to put the hand down.
Okay, no problem. Okay. But while we're at it, actually, I have a question, if you don't mind, Jorge.
Sure, please.
Okay, so do you view it as a feature or a bug that could I trouble you to go back to the previous slide where you have the Q's in the anti-commutator?
Okay, let me try to go back. No, here.
Yes, exactly. So, is it a feature or a bug that the Q's when put into the anti-commutator, they didn't close to SO31, but you needed SO32.
The fact that you need this, yeah.
So would you have preferred that it would have been SO31 or? So in the end, you get back down to SO31 by the Hodge dual, or this by the action is invariant under a smaller right. Group. So I guess what my question is, it seems like there might be another way to go about it, and I don't know if it would work or not. But so you can cut down to SO31 by using the Hodge dual. In this Yang-Mills action, or I wonder, would it be possible to come up with another kind of multiplication rule for the Q's so that they wouldn't include the FAJA term?
Okay.
So instead of a simple anti-commutator, perhaps something something else?
Well, the algebra requires this. That's one thing. You can check by the number of matrices that you can produce here. This has some symmetries, and checking all the indices, you see that you need a certain number of them. So that's a reason why you need also the U1 piece. I mean, this algebra would not close if you didn't have the Z. And it wouldn't close in 4 dimensions if you didn't have the J. That's because the number of components of the Q's grows with the number of dimensions and grows as 2 to the n over 2 or something. So it doesn't grow linearly. If it grew linearly, you may be able to get away with only this piece. But you need also this piece because there are more Q's around. So you need more bosons to close the algebra. Well, that's an experimental fact, if you wish.
Okay, so that's not assuming in anti-commutator like a normal the standard anti-commutator and commutator multiplication rules.
Yeah, it is a standard thing. I mean,
I know, but I'm asking, would it be possible to
do something else? Well,
to
you can
generalize
check
it so
other
that
things.
it closes on the smaller on the subgroup?
Yeah, we tried and we looked around and we found that in all cases, the supersymmetry algebra in this form and this representation requires this piece. Maybe if you have Majorana spinors or some other reduced form, maybe Weil spinors or something, you could also get rid of some of these things. But actually what happened when you have Majorana spinors is that you can get rid of this, but we could never get rid of this. We didn't find it, and maybe there is a theorem, maybe one can prove it, but we were just frustrating looking for that. And all we found in the literature is that this is the supersymmetry algebra in, I mean, the only thing that you can do is change this 2 into 1, and if you use Majorana spinors, but you cannot reduce the OSP4 further to only include the Lorentz part. I mean, maybe you can explain why, or maybe there is a theorem for that, but that's all I know so far. Now, in the case of, if you try to play this game without this part, let's say you eliminate the fermions and the internal symmetry groups, so you just take only the space-time part, so you don't have this problem. But try to find a Lagrangian just for the anti-de Sitter group. And you will find that there is no invariant trace that does the job. There's no invariant Lagrangian for these fields, for omega and F, that is invariant under SO32. And that's essentially a reflection of the Chern-Weil theorem. If there were an invariant of SO32 in 4 dimensions, it would be a topological invariant. So in order to have a Lagrangian, you have to break parts of the symmetry. So there's no, if you want to find a trace that is not a total derivative, then you have to reduce the symmetry from SO32 to its largest subgroup, and that is SO31. That's the status of the thing, anyway.
Okay.
Okay. David, you have a question? Oh, no.
Me?
Okay. No, I thought there was also a question.
Another question.
Another question. Okay.
Thank you.
So this is the situation. You have this Lagrangian. This is the combination of internal symmetry, fermions, and space-time symmetry of space-time parts. This is invariant under this this largest subgroup, and that is internal symmetry under Lorentz group. So you don't have invariance under either supersymmetry or invariance under the entire anti-de Sitter group. Now, the Lagrangian that you have, since this field is no longer a connection, you can solve its field equations or equations of motion algebraically, and this is a solution. You can plug that into the action, and this is the effective action that you get. You get a Lagrangian which is boringly familiar, is essentially the Maxwell or Yang-Mills action for the internal symmetry group. It has the Dirac term. There is also a torsion coupling between the fermion and the spacetime torsion. And there is the the Einstein-Hilbert action for the anti-de Sitter background for the with cosmological constants. So this R epsilon RR is topologically invariant. The cross term gives the Einstein-Hilbert, and the four field bound term is essentially the cosmological constant. And there is an additional term, which is this Nambu-Yonah-Lasinger term, which is also coupled in the system. But apart from that, it's essentially the standard low energy description of gravity with an internal symmetry and a fermion coupled to them. Now the couplings are the standard couplings. The covariant derivative appearing here is essentially the ordinary derivative with the right connection terms. There are no higher derivative terms for the fermions. The cosmological constant is negative, and Newton's constant is related to that. So this is essentially the only new novelty in the model, that there is this Nambu-Yonah-Lasinger term, which is predicted in this case. Now, this is okay phenomenologically at low energies in 4 dimensions for this simplest case that we can write. Now, let's see what happens with supersymmetry. Why is supersymmetry not seen in the experiments, or where should it be seen? Now, it turns out that in 4 dimensions, in the case I just mentioned, the only invariant 4 forms are characteristic classes. And if you want to make them invariant under the entire gauge group, and this is essentially the Chern-Weil theorem. So in order to have something that has is not a topological invariant, you have to break down the symmetry to a smaller group. And this is essentially what the Lagrange, this Hodge dual does in this case. But now, since the spacetime symmetry is broken from anti-de Sitter to Lorentz, it means also that supersymmetry is broken, because the algebra now doesn't close. So the largest surviving supersymmetry turns out to be the internal symmetry on the Lorentz group, and nothing else. There could be supersymmetric invariant vacua, namely, there could be configurations of a space-time where the larger symmetry can exist if you're lucky. But this is not an invariance of the action. It could be an invariance of the states. So local supersymmetry could be an approximate symmetry for some configurations or in some regions, in the same way that the Poincaré or the anti-de Sitter invariants are invariances of states and not of Lagrangians. So this is what we call a contingent symmetry. It's a symmetry that depends on the background. Now, in odd dimensions, you could play the same game, and I wrote here the transformation laws for supersymmetry, just to explain what happens. So if you have a supersymmetry transformation, this bosonic internal symmetry transforms like this, the Lorentz connection transforms like this, and the fermion transforms like this. Now, in this case, the Vierbein doesn't transform, and this is like in Yang-Mills theories, where the metric doesn't transform. In general, the metric is given, and it's not, the metric structure is not very changed under gauge transformations. Now, all of these can be combined into a transformation for the connection that is essentially proportional to the gradient of the parameter, the supersymmetric parameter. Now, this changes the action, as I mentioned, by a boundary term. However, the condition that this fermion has to satisfy, this parameter has to satisfy this constraint. Now, this constraint means that you have to restrict the spin of the excitation to be a spin 1/2 excitation. If this is a spin 1/2 excitation, in general, this could contain a spin 3/2 component. And the restriction here requires that the spin 3/2 component is killed. Now, some backgrounds may satisfy this equation. Some backgrounds may not. If the background satisfies this equation, then this supersymmetry is a symmetry of this configuration. If it is not, then the supersymmetry is broken. Now, the fact that this symmetry exists corresponds to the fact that this state or this background is a BPS state. Now, for instance, the configuration psi equals 0, the purely bosonic vacuum, would be invariant provided this epsilon has satisfied this equation, and this means that epsilon is a Killing spinor. Now, manifolds allowing for a certain number of Killing spinors means that there is the same number of unbroken supersymmetries in the background. Therefore, the fact that supersymmetry exists is a conditional property of the background. It depends on the vacuum you're working with. So let me summarize a bit, because I don't want to overdo this. The idea of this form of understanding supersymmetry starts with this observation that an adjoint representation and a fundamental representation can be combined into an adjoint representation of a larger group. Then you can use this to put the connection and all the other fields into a connection by itself, where you have space-time symmetries, internal symmetries, and fermionic generators. This superconnection, we include also this assumption that the fermion, the one form that appears here, is actually a combined object of a field bind and a Dirac matrix and a spin 1/2 field, where this spinor now satisfies this constraint. In addition to this, you need an invariant trace, and in the case of even dimensions, you need to include also the Hodge dual. And with all these ingredients, you can construct the action that you wish for the group that you want. Now, what are the consequences of this? Now, all the fields become part of a superconnection. So matter particles, fermions, and interactions, that is bosons, combine in the right way. They behave as sections and connections of a gauge group, and they are packaged into a single object. Now, not all space-time symmetries are allowed. If you have an SO27, you may need some connection that allows for that, but if you want some other strange symmetry like Poincaré or conformal symmetry, it may not be allowed. Now, only spin 1/2 and spin 1 fields are included. There's no spin 0 or 3/2 or spin 2 fields. All of these can be composites of the original fields. The kinetic terms are always of the standard type for Yang-Mills, for the Dirac, and for Chern-Simons forms. Only the standard couplings appear. So, for instance, the Yukawa coupling appears, but weird things like this do not exist, do not occur. There are no supersymmetric partners and no pairs of bosons and fermions in equal numbers or other strange things that have not been seen. Now, there is a question, there is a raised hand by Legender.
Yeah, thank you. Yeah, this is very nice. This takes me back to the first question. So this is a good thing, this super connection. Can I write now a Lagrangian, an action principle, which depends only on A?
Sure. In the case of Chern-Simons theories, yes, you can. You don't need anything else.
Yeah, could you please, you have it anywhere in your slides? What does it look like?
Yeah, the case in 3 dimensions is like that.
But for 4D?
No, in 4D you need this additional object. You need the Hodge.
Okay.
You need also this. In 3 dimensions, you only need the trace in the algebra. In 4 dimensions, you need in addition the Hodge.
Okay, thank you.
And then it's like a Yang-Mills action. in that case.
Okay, that's good. Thank you. Thank you.
Yeah. So what is new in this model? It seems to be giving you back the same stuff, the old stuff. Well, it does relate the coupling constants and the masses. I mean, they're not arbitrary. They're not arbitrary parameters. They're all produced by the construction of the Lagrangian. As I said, the action is invariant under the gauge supergroup because it changes by total derivative in all dimensions. And even in dimensions, the action is in general not SUSY invariant. It will depend on the background. Now the vacua, like f equals 0, will have the full supersymmetry and full symmetry under the complete algebra. There is always an unconventional term that appears, which is puzzling. It has some phenomenological implications. Probably it's related to non-renormalizability or generation of mass gaps and all that. In all these models, gravity is necessarily included because the spinors require the field bind and because the Lorentz symmetry produces spin connection. Therefore, you get always gravity. And in fact, gravitational Lagrangian appears in this case. Now, what is the role of supersymmetry in all of this? Now, it seems that this construction relates spacetime and internal symmetries in a natural way. So it does fulfill the purpose of supersymmetry. The superalgebra, the gauge couplings, and the coupling constants, and all of these are required by very few requirements. I mean, they're defined by the dimensional spacetime, the internal symmetry group that you want to accommodate, and essentially that fixes the rest. It tells you what space-time symmetry groups are compatible with that. Now, the presence of gravity is necessary in all these cases. The invariance of the gauge symmetry of the action is essentially an internal symmetry group in all cases with the Lorentz group and nothing else. There's no other invariance. There are no larger invariances of the action. Now, the invariance under the entire supergroup can always be obtained in some vacua, which are the BPS states. But apart from that, it's not generally true. Now, there are open questions. What are the observable effects? And for instance, one is a thing in what happens, for instance, in graphene. What does supersymmetry imply for the graphene sheet? For instance, what happens with the vacua? What are the consequences, perhaps in the spectrum of graphene? What happens with renormalizability? Are these theories renormalizable? We don't know. We haven't completed this checking. It's actually very hard in the case of gravity, in the case of 4-dimensional, because you have gravity, you have unconventional terms and many other things. So one must find a clever way of understanding this. The other question is whether this does something that supersymmetry is supposed to do, which is protect the hierarchy. So if there is a scale, the mass scale in the theory, is that going to be respected? We don't know. Now, we don't know how to play this game with groups which are more complicated, like SU1, SU2, and SU3 together. We know how to do U1 and SU2 or U1 and SU3, but all of three of them together, we don't know. So maybe as Nichol has some, perhaps she has some insights of how to use octonions to play this game. Now, the other thing is that in the matter ansatz, when we do this, we reduce the spin 3/2 field into a spin 1/2 field. And if you do that, you can do this in any supergravity theory where you have the Rarita-Schwinger type of coupling. And if you substitute here this chi-mu, what you get is essentially the Dirac theory, the Dirac term. Namely, it seems that in all supergravity theories, you can have an unconventional supersymmetry lurking in, because there's always a spin 1/2 theory that can be obtained for any supergravity theory in this manner. So it seems that perhaps we have been dealing with the supersymmetric theory of this type for a long time, but we have been looking for the wrong signals. We've been looking for equal masses or supersymmetric partners and stuff like that, maybe it doesn't happen. We don't have any evidence of this in this model. So perhaps the fact that supersymmetry is dead is also an exaggeration, and as Mark Twain used to say about his own death. So that's it. Thank you very much for your attention.
Thank you so much, Jorge, for a wonderful talk. I think we actually already have a question here by David. I'm just going to unmute you, David.
Yes, David.
Yeah, thank you for the talk. I just had a question about your comment for going beyond the electroweak sector. I mean, if you look back at the work of Kaku and Townsend from back in the day, they worked for arbitrary SUN for internal symmetry. So I believe that would work for you as well. I was studying your work and looked into it, and that seems to work. So you could look at SU5 and have that as an internal symmetry, and then presumably break that to the standard model, don't you think?
Yes. In fact, we just put up a paper on SUN. So if we did something that you used just SUN and the supersymmetric extension and trying to play that game, but what I don't see clearly is how to break down SUN into these three pieces. Why the representation should come in this manner. That's essentially what I'm confused about. But you're right. I mean, this could be done for SUN in general.
Right. The key is the Higgs, because yeah, you can't stay in McDowell-Mansouri gravity forever. At some point, you need a Higgs, and that would be what breaks it. Yeah, definitely. Thank you for the talk.
Yeah. Well, rather than the Higgs, I would prefer the other thing, the Nambu-Jones term, because that also generates a mass gap. Actually, that's the way you generate mass gap in superconductors. Is using that, well, the Higgs is some sort of phenomenological effect that does the same thing, but it doesn't come in a fundamental manner as the Nambu-Jones term does in this case.
Okay,
Andreas?
so it looks like, yes, Andreas.
It's a perfect transition to my question, because I wanted to ask, since, I mean, how general is the statement that you don't get the S equals 0 state? Because if we now believe that we have seen the Higgs as a, rather fundamental looking S equals 0 state, how do you, I mean, I understand that you get the mass terms from this NGL terms, but you still would need some scalar excitation, right?
Yeah, well, you see the Nambu-Jones term does that, because essentially when you have, for instance, chiral symmetry breaking, and this is what happens in superconductivity, that generates a vacuum expectation value for psi bar psi, which is essentially the mass term. So you generate a mass gap, and that comes from the fact that in the case of superconductors, it comes from the fact that this is a non-renormalizable term. So the expectation value, or the vacuum expectation value of psi bar psi, has a scale that is proportional to the cutoff. Now, if the theory is non-renormalizable, in the case of a superconductor, this cutoff corresponds essentially to the Curie temperature, the temperature where the metal sort of becomes something else. And since the mass term is essentially proportional to the logarithm of that, it doesn't matter whether the temperature is 1,000 degrees or 10,000 degrees, the logarithm doesn't change much. It generates a mass term that is essentially a few degrees Kelvin. And that's why you have in a superconductor, a superconducting phase at very low temperature that is related to the cutoff at very high temperature. So in this case, perhaps the cutoff could be the Planck mass. And still you could generate a very small mass because it's logarithmic on the Planck mass. So actually that's another mechanism for producing mass without the Higgs. So
sure, but I mean, you still have to, I mean, you would have a fundamental Higgs then. So at some point there should be, the more we investigate the Higgs, the more, I mean, at some point you should see a deviation from
sure.
Yeah.
Sure, of course, yes, you're absolutely right. Yes.
So could this be, I mean, so does the statement, I mean, you mentioned the possibility that you could have also marry this in some way to conformal symmetry or scale symmetry. Has this been looked into, and does this S equals 0 statement also hold for them, or could you have a fundamental S equals 0 guy as say dilaton or scalaron?
Well, I don't see very naturally a zero form or scalar in this picture, because we could, I mean, all these things come in from one form from a connection. So unless you find something like a composite or a condensate or some other combination of fields, like this, in this case, psi bar psi or some other stuff, it's not easy to produce a scalar. Scalars would not be fundamental fields. The same is true about spin 2 fields. The graviton is not a fundamental field in this picture. The graviton is some sort of effective product of two field lines. So it's a different philosophy, if you wish. Scalars are not the simplest object in this construction. Simplest objects in these constructions are one forms.
Thank you. Very interesting. I really like it.
Thank you very much. So there are more questions, I think.
Yes. Okay. So Tejinder.
Yeah, thank you. Very nice talk, really. Thank you. So I had two questions, one of which you actually already addressed in your last remark in passing. So for you, the graviton is a composite effective object, and you mentioned Furey. So are you suggesting that, like the standard model gauge bosons, gravity do you want to associate it with underlying spin 1 objects?
Yeah.
And then after that, I'll come to the second question. Yes, please go ahead.
Okay. Yeah. Let me try to see if I can change my screen or my camera. Oh, well, it's very hard. Anyway, it's the thing is the following. I'll write it down here. Can you see this?
Yeah, yes.
Yeah, is that the metric is essentially a composite.
Yes, of course.
Pure field lines.
Yes.
So you don't need this as an independent field if you have already this.
I agree. So
if
no,
you have the dynamical field, then this is going to be a composite of that.
If I quantize the Furey, would I associate spin 1 bosons with it?
Probably, yes.
That's very interesting. Thank you. Thank you.
Sure.
And the other question was, how does the number count of bosons and fermions go? Are they equal in number? Because the standard model have 3 fermion generations, 12 gauge bosons and a graviton. How do I expect some number balancing to come out?
Well, that's a very good question. It also is probably related to the representations that you're working with. But one thing is for sure different from a standard supersymmetry, that you don't have equal numbers of bosons and fermions, which is also something that you don't see in a standard model. There are no equal numbers of fermions and bosons anywhere.
Could it be 1:3 or 1:4? You expect?
Yeah, well, it depends on the representations. The representation for fermions go with 2 to the dimension by 2 divided by 2, and the components of a representation of a internal symmetry go as, I don't know, the dimension of the adjoint representation, typically n squared minus 1 or whatever. So there are no particular relations connecting the two.
Okay, thank you. Just one last remark on the first question, because you're one of the rare persons who are saying that graviton is effective and not fundamental, and I really support that. Should experimentalists be looking for spin 1 gauge bosons mediating pre-gravitation and not look for the graviton?
Maybe, yeah. But in order to see that, you have to be, I mean, you should be able to do experiments with gravity at very high energies and very short distances.
Yeah,
that I agree. visibility
Yes.
yet. Yeah.
Yes. Thank you.
Okay. Okay, Alex.
Yes. Boson has spin 1. What does spin graviton have? And will gravitational wave experiment help to verify the theory?
Well, I don't know if the gravitational wave experiments can measure the spin of the excitation. I'm afraid it's a very complex. I mean, a gravitational wave, a classical gravitational wave, is like a classical electromagnetic wave. I don't know if from a classical electromagnetic wave you can determine that the photon has spin 1. I suppose it's that type of difficulty. I really don't know how experimentally you could determine the spin. This is
Yeah,
really,
because a little different issue. Electron spin 1 or proton spin 1, wave spin half. No. Photon spin 1. Yeah, you're right.
yeah.
Graviton not should be spin 2. Probably there also should be particle with half spin, like for electromagnetic field.
Could be. I have, but I suppose that depends on probably on the model that you have to describe gravity. I mean, to me, gravity looks like a. Excuse me.
Okay, thank you.
But what I was saying is that gravity is a theory that we know describes space-time on large scale. In that sense, it's like classical mechanics. It's a classical theory. We don't know what the fundamental Lagrangian of gravity is. Is this as if you were working with soap bubbles, you know? And what you find is that the equations for a soap bubble tells you that the surface area is a minimum. It's a minimal surface for a given boundary condition or a given volume. So soap bubbles that enclose a volume are spheres, and soap bubbles that are spanning a loop are curves of constant curvature. Now that it could be obtained with many fundamental theories. Soap, I mean, the chemistry of soap is not entering in that expression. We don't know what soap is made of by studying soap bubbles. We only study the geometry of the soap bubbles, and we can write down a beautiful Lagrangian for that. But we will never learn about the chemistry of soap. So in the same way, we know the equations, the Einstein's equations that describe gravity, and they're wonderfully fit for that, but we may not be able to infer from that what is a microscopical theory for gravity. Maybe we will never learn by just looking at the Lagrangian for gravity. I don't know, I'm a bit pessimistic about approaching quantum gravity from the classical Lagrangian. I don't think that it's a very fruitful way.
Yeah, okay, thank you very much.
Sure.
Does anybody else have any more questions? Thank you so much, Jorge, for such a wonderful talk. That was really clear and yeah, and really informative. And yeah, thank you to everybody for your questions. It's a lot of good questions today. Okay, yeah,
Thank you, Nichol, for the opportunity and for the many questions that I had. Thank you. Thank you all.
Yeah, thank you. My pleasure. Okay, so our next speaker is Markus Müller at the Institute for Quantum Optics and Quantum Information in Vienna. On the 28th of March, Markus will be giving us a talk on quantum theory entitled From Principles and Thought Experiments to Jordan Algebras. Okay, so thanks again to everybody for showing up and for your great questions, and especially to Jorge for giving such an interesting and understandable and clear talk. And I hope to see everybody again in the next couple of weeks.
Thank you. Bye-bye. Thanks.